So today I'm going to tell something to do with superposition, quantum addition, and quantum coherence. And this is the recent work we have been doing, and I will tell you some partial results in this context. So superposition, as you know, is at the heart of quantum mechanics. That tells you that if you have two possible quantum states like psi 1 psi 2, then it is also possible for the physical system to remain in a state which is a combination of alpha 1 psi 1 plus alpha 2 psi 2. And also we know that quantum theory allows the particle to behave not only like a particle but also like a wave. And this is a cartoon which tells something about the self-identity of photon. Photon doesn't know whether it is a particle or wave, and also doesn't know where photon is, and so on. So this is the old problem of wave-particle duality. And this is beautifully paraphrased by Richard Feynman, which tells you that in reality it contains the only mystery. So, and that is also seen in this standard double slit experiment. You have a source and you have a double slit in front of the source, and you send particles one by one. You put a screen, and if you wait long enough, you see the interference. And that you explain by assigning, okay, the wave function on this screen at any point is a combination of psi 1 plus psi 2, where psi 1 and psi 2 are the wave function corresponding to the two slits, 1 and 2, and then the interference you can explain by saying that the probability of finding the particle at any point on the screen is given by this. So this is the distribution due to slit 1, distribution due to slit 2, and this is the interference effect. And the interest still continues, as you can see the work by Urvashi and others, where they try to prove the accuracy of Born rule, and even they ruled out the multi-slit, multi-order interference in this kind of quantum interference effect. So for pure state, as we will understand, it is natural that quantum coherence arises from coherent superposition of different amplitudes. For mixed state, there is no such notion of coherent superposition of mixed state. Okay, all you can have an incoherent superposition of, say, rho 1 or rho 2, or even more, density operators in this context. So a priori, it is not very clear how quantum coherence can arise from the superposition of principle for mixed state. So whenever you think of this, typically it refers to a physical system, and that physical system is in a pure state. But nevertheless, you can do an interference experiment with mixed state, and actually you can see the interference visibility, interference phase shift, and so on. For example, if you have a Mach-generated interferometer like this, you send a mixed state and put a beam splitter and mirror and so on, and put a unitary operator on one arm of the interferometer, then you can see the interference that is governed by the phase shift, which is given by the trace of rho u, where rho is the input state and u, this u sitting in here. This was, it was not easy to define this interference and phase shift for mixed state that were done by our group in 2000, and many people did experiment and actually verified this phase shift in this interference experiment. And also Professor Anil Kumar and his student, they also did with NMR in 2006. So you see, like pure state, also mixed state do display interference if you suitably design such a setup. Okay. So the question then is, how come coherence can arise in mixed state? So as I said, given two mixed state rho and sigma, you can mix in a stochastic way. You cause a tau n with probability alpha, you have the state rho with probability 1 minus alpha, you have the state sigma, and you add this in a you have a converse combination of this two density operator. But there is nothing quantum about this kind of stochastic mixing. Okay, but is there any other way to add two mixed state quantum mechanically? So that is the question that we are trying to ask, and we are trying to look at various literature where such a thing is possible, and indeed there is such a way to do that. So that is the main focus of this talk today. So that is the quantum addition, which is different than the classical mixture of two density operator. This quantum addition allows us to mix two quantum states that is different than classical mixture, and that includes an additional contribution arising from the non-commutativity of the mixed state component over and above the classical mixture. So the main idea that we are trying to play around in this, the work that we are doing with one of student and one of my postdoc is for mixed states, the quantum coherence may arise from the discrepancy between quantum and classical mixture. That is the essential idea that I will try to convey to you, and I will actually try to tell one or two instances where actually this is true. So what is this quantum addition? So before telling that, let us go back to last century, to the era of Shannon in 1948, where he tried to prove something called entropic power inequality. So given two random variable x and y, he tried to prove that this inequality hold, that is exponential of hx plus exponential of hy is bounded by this for any continuous random variable. And there are many numerous proofs for this kind of inequality proved by Shannon and also by Sturm in 1965. And this kind of entropy power inequality is useful in finding upper bounds on the capacity of certain noisy channels. So why this is called entropy power inequality? Because originally Shannon considered a Gaussian random variable, and for Gaussian random variable, if it is having zero mean and say variance sigma square, then the Shannon entropy is connected to a logarithm of up to some scale factor logarithm of the variance, and variance typically referred as power, so that is why this is called entropy power inequality. And recently in 2014, these people Koenig and Smith, they tried to prove this quantum analog of this entropy power inequality for continuous variable system, but the proof essentially depends by and large same techniques as was originally used for classical random variable. But what about finite dimensional system like qubits? So that was the thing that looks very interesting to us. And again in 2014, Datta and collaborators, they tried to define something called quantum addition channel, which looks like this. Given two density matrix rho and sigma, you add according to this rule. I will tell you what this rule is. And in the output, what you have is alpha rho plus 1 minus alpha sigma minus this thing times the commutator of rho and sigma. So you see, this is something different than the classical mixture. Classical mixture will only allow to have this and this, not this. Okay, so that is why they call it this quantum addition. The quantum addition takes into this fact that rho and sigma could be non-commuting. If they commute, then you have the classical mixture. Okay, so this is clear. I mean, the word, this terminology quantum addition is self-explanatory in the sense that you have the additional contribution coming due to the non-commutativity of rho and sigma. And this is discrete analog of beam splitter action for continuous variable system. How do we achieve this? This is not just some mathematical, axiom or something, or is a statement, but you can actually realize as a physical process. So to realize that, what you have to do is to show that this is indeed a completely positive trace preserving map or CPTP map. So what they prove is that you have a input rho, input sigma, you take the tensor product and apply this U in trace of the second system, and in the end what you have is addition of this rho and sigma according to the rule given by this. Okay, and what is this U? This U is essentially a partial swap operation, because that unitary operator interpolates between the identity and the swap operation, as you can see here, that is given by this. So square root of alpha identity plus square root of 1 minus alpha times the swap is the global unitary that will actually realize this CP map, and will will result in the state rho addition of sigma. Okay, so this is something very nice and very beautiful, because you can actually physically realize this. So the main result due to the data and others is the following, that they prove that for any concave function f of rho, the quantum addition of rho and sigma is bounded by, lower bounded by the convex combination of f of rho and 1 minus f of rho and f of sigma. And from this main inequality you can derive this kind of thing, or even for this kind of thing. So if you choose this f as the von Neumann entropy, you have the S of rho addition sigma is bounded by the convex combination of S of rho and S of sigma. Sorry, the typo here should have been S of sigma. And if you use exponential S of x, then you can have the entropic power inequality for qubit or for any finite dimensional quantum system. And recently this was conjectured by Zhang and others. What they tried to prove is the following, that given this quantum addition and given a classical addition like this, which is more or which is less, okay. So they tried to prove that for certain value of alpha, like alpha equal to half, that the quantum addition is, the entropy of quantum addition is always lower than the entropy of the classical addition. But they leave this as a conjecture, that for any alpha they could not prove this. So our one of the main result in this context is the following, that we try to prove that for any alpha this is true, that the entropy of classical mixing is always more than the entropy of quantum mixing, okay. So quantum, if you add two density matrix in a quantum mechanical way, then the entropy is always less compared to what it would have been if you had in a classical way. So the proof depends on this. You take the difference of this and this, classical mixing and quantum mixing, and that is essentially equal to the relative entropy of this and this, and that settles the conjecture recently put forth in this paper, and that is the starting point of our investigation in this context. So we look at this term. So here is a proof, but don't worry about the proof. The second, essentially this difference turns out to be this minus this, and that goes to 0. So this, our main focus is the difference between this and this, the entropy of classical mixing and quantum mixing, and that is essentially this relative entropy of these two density matrix. So the question is the following: can this difference capture some quantumness? Okay. So quantum way of adding two density matrix tells you that entropy is less compared to classical way of adding the two density matrix. So this extra randomness that is left over, can that capture some quantumness? That is the question that we are trying to address here, and we will show that indeed our guess, our hint is, idea is true. But before that, let me tell you briefly about this notion of quantum coherence. So even though 100 years have passed since development of quantum mechanics, this quantum coherence as a resource theory was developed very recently in 2014 only, very recently by Plenio group. And as you know, in any resource theory, you have to identify some free states and free operations. Okay, so free states are those which are diagonal in a given basis, and free operations are those which are incoherent operations, and they will map incoherent state to incoherent state. Not only that, every Krauss element should individually map incoherent state to incoherent state. So once you identify your basic ingredient of the theory, then you can develop the resource theory. After this paper, there are many other development and many other way of defining this incoherent operation, but that is not our concern here. So the original paper tried to try to set certain axioms. First is the following, that for any incoherent state sigma, this coherence measure should be 0. That is obvious. And for any other state, C rho should be positive quantity. So if this is true, then you will say that that state rho has a finite amount of coherence. And there is some condition called weak monotonicity under incoherent operation lambda, that if you apply lambda on rho, you should never increase the coherence. And also there is strong monotonicity under incoherent operation that tells the following, that if you apply ki on rho and you have the state sigma I, on the average again you should not increase. And the final desirable property is the following, that for any density matrix rho, the C rho should be convex, that is should be bounded by Ei Cf rho I. So any object that you can identify and you can prove that that object satisfies all these properties, then you can say that is a valid measure of quantum coherence. Okay. So in this paper, they try to prove that indeed there is something called relative entropy of coherence and L1 norm of coherence. They satisfy all these properties. Okay, so they are very good measure of quantum coherence. And over last 4 years, there has been extensive amount of work, in trying to understand this coherence and all these features. So, what is the main thing that we want to convey here? We want to say that the difference between this classical mixing and quantum mixing, can that be a measure of quantum coherence? So first thing we tried the following, that we tried to minimize over all incoherent state, take sigma as an incoherent state and minimize over all such thing. And surprisingly, you could prove all the properties, but then it becomes a trivial thing, because if you choose sigma to be maximally mixed state, then this will be 0, which is not a, you want something finite quantity. So this is something you don't want. So this is not a good measure of quantum coherence. So other option is the following, that you can try to maximize over all incoherent state, and you could also take average over all incoherent state, and maybe that will be a measure of coherence. But we don't know, we're still working on this. Maybe I should tell that if you have a definition which maximizes over all incoherent state, in this definition, for example, you take the difference, this relative entropy of quantum addition and classical addition, and maximize over all incoherent state, we could prove only one of the properties, that is convexity. Remaining things are very hard to prove, so we don't know whether we can do that. But anyone else here in the audience are welcome to write to us if you have any idea. But instead of that, we tried the following, that if you take a trace distance between this quantum addition and classical addition and maximize over this incoherent state, then we could show that at least for q bit and q dit, we could show that after some scaling, this is exactly the L1 norm of coherence. Okay, so the proof is here, but again, don't worry about the proof. The essential thing is this trace distance is CL1 times this square root of alpha 1 minus alpha. So up to this factor, this is exactly the L1 norm. This is something beautiful, and also it fits to your intuition that this difference, when I say difference, it could be in some distance measure, it could be some relative entropic measure, or some other measure. Okay, so this difference, can it capture the quantumness or coherence? The answer is yes, indeed it can do that. Okay, that is the main message, and but if you take the original definition of relative entropy, this thing, and maximize over this incoherent state. Here, instead of minimization, if you do maximization, then that is connected to relative entropy, that is guess, but we don't have a proof. So only we have some numeric example which suggests that that is bounded by a linear function of the relative entropy of coherence. Also, you could prove for higher dimension, this trace distance is also bounded by, actually linked to the L1 norm of coherence even for higher dimensional system. So things we are trying to explore are the following. We are trying to construct a genuine coherence monotone from the discrepancy between quantum addition and classical addition. And also you can ask the following question: what does the discrepancy between quantum addition and actual superposition for pure state capture? Because these two things are different, even though this looks like superposition, but it is not. So for pure state, these two things can be different. For mixed state, you have only quantum addition, you have classical addition. For pure state, you could have classical addition, you could have quantum addition, you could have also superposition. You see, so the difference between this and this, can it capture something else? We don't know that. So any additional quantumness or non-classicality, can it capture that? Still you have to think about that, and we're still working on that. And also creation of quantum coherence, or like other resource using quantum addition, that is still ongoing. And maybe I should also mention, this is the thing that I presented here is done by one of my students who is present here, and also one of our postdoc who is also present here. Along with that, I've been discussing with Shivashish Ghosh, who is also here from Med Science. We're trying to understand what could be analogous of entropy power inequality for coherence. So if you're having a quantum state and sending it from channel, yes, I'm almost done. So can you prove something like entropy power inequality for coherence? So that may be something useful and may have some application, but not much progress has been done. So yeah, so a lot of open questions are there in this context. Okay, so with this I thank you. Yeah.
Thank you. Questions?
It was very interesting idea. So 2 questions.
Yes.
One, you have some extra randomness generated due to quantum addition. Have you tried to quantify that extra randomness? So it's whether in terms of randomness generation, it can have any application.
Yeah,
so that seems to be obvious to compute how much more random. You did not mention that, but it's a quantitative aspect of that randomness.
No, we're doing that. So
okay.
Still in progress.
And you say if you start with maximally mixed state classically, can you do quantum addition for that? And
yeah, but then it's trivial. You
don't get
zero classical addition.
So quantum addition of pure states, does it also yield extra randomness?
Yeah,
no.
Yes.
It also yields.
Yes.
So that would be especially interesting
So
in terms of randomness generation.
Yeah.
Okay.
The process of classical mixture, as you showed mixing of drinks, is taking 2 states and putting them with certain probability, which means you can create a mixed box in which you put both those with certain probabilities. How do you do quantum addition?
Yeah, so you take 2 density matrix rho and sigma, apply this U, okay, and then trace out the second system and you get the quantum addition. So it is a physical process, valid physical process. So you can imagine like this, there is a box.
So you are taking 2
states. There is a box, 2 input, rho and sigma. You apply U in that box, okay, and then discard the second qubit.
Yeah,
what
so
will go
therefore,
out is your rho sigma.
So therefore you have to work in the tensor product of the 2 spaces. Right?
Yeah.
So why is one comparing it with then mixing?
No, it is.
This is taking 2 quantum systems, doing a certain unitary operation in the tensor product Hilbert space of those spaces, and then tracing over one. Yeah.
So there is a connection between quantum and classical mixing, because if you rho and sigma commute, indeed you get classical mixing.
I understand. So it's a well-defined operation. All I am saying is that why is it being suggested as an alternative to classical mixing? Because that is not in the tensor product space.
Which one is not tensor product?
The adding of 2 density operators.
In classical way of mixing.
Yes, that is saying that you have 2 different states and you put them with some probabilities in a box and you create a mixed ensemble.
No, I mean to realize the classical mixing also you can realize in a unitary way. I mean you can take rho tensor sigma, add ancilla, and discard the second qubit and ancilla. You can still get the classical mixing.
That's a roundabout way of.
You see, everything you can because that is just a physical process. You can also enlarge Hilbert space and do everything in a bigger Hilbert space. So that is fine. So.
No, the composite nature. I mean, you don't read. You can have the same space and have several density operators defined in that. You need not bring in. Because for the swap operation, you have to have then a possibility of this kind of 2 spaces coming into the picture, right?
Yeah.
Arun, Feynman had a identity of this kind which he used to estimate the Polaron mass.
To estimate what?
Polaron mass. This exponential kind of identity which you are mentioning. Feynman had used similar kind of identity to estimate the polar mass quite accurately. Have you looked at that?
No, I have not seen that.
Have you not?
No, I can think of the incoherent addition of two states as drawing a straight line between them and taking a point which is alpha from one, and one minus alpha from the other. Now, it's possible to generalize this idea in many ways, given any metric on the state space. And there are several metrics. For example, there is the Bures metric or the BK metric.
Right.
I can take 2 points, join them by a geodesic, and take a mark a distance purely geometrically. And what I would like to ask is, why is this particular definition of quantum addition more significant than any other? Like, for example, Arvind was asking the question, how do you operationally realize this notion of quantum addition?
Yeah, so no, operationally is well defined. So the question is, why this is the only way? That probably they don't, the origin authors don't know. They just tried this and then, they could prove the analogous entropy power inequality. Their motivation was different. We are taking that and trying to see whether that can have some implication in this context, but their motivation was something different, completely different motivation. So they tried to prove the analogous entropy power inequality for finite dimensional system. So they could do only with this, not with some other way of doing it.
I understand that. My
So
question is,
there could be other way, yeah.
well, my question is only what distinguishes this particular measure, this particular operation over others one can think of. That's really the question.
Yeah, I don't know, but we can try, certainly, yes, yes.
Yeah, well, no, so my question was somewhat similar, that there are infinitely many ways of defining a partial swap gate that, with a single parameter such that at one end it's a swap and at the other end it's an identity.
Right.
And so what distinguishes the one chosen here?
So what distinguishes from what?
What distinguishes the one chosen here?
No, with this particular unitary, they could see that they have this particular way of quantum addition and they could actually derive this exponential h of x, exponential h of y is bounded by this. So, that is the only thing they aim for, and they could do that.
Sorry?
With this particular way of quantum addition, they could prove, as I said, they could prove the entropy power inequality. With other addition, they could not, as far as I know, that I was saying that they could not prove with the other kind of addition. So, probably that is the only thing I know. So you will get, yeah.
So you considered mixed states in continuous variable systems. So
no. This is everything what I said only for finite dimension, not continuous variable.
Oh, really? Yeah.
Yes, yeah.
But is it possible to apply your idea to the qubit systems, such like qubit? So
Qubit.
A mixed state in qubit systems, such
Exactly,
like
yeah.
electron spins or photon polarization.
Yes, of course. Yes. Yeah. Everything you can apply. Yes.
Okay. Thank you.